Okay, welcome to another video. We'll be starting on a series of videos here called Integration Methods for Calculus 2. I think these are the most useful ones to teach in a straightforward video where you aren't trying to complicate it, because a lot of teachers try to complicate this and make it seem more difficult. I think that makes it harder to learn and appreciate because they actually are a lot of fun once you learn them. So the integration methods are going to use a lot of basic derivative and integral foundational things. So if you don't know things like the power rule, go back to a different video and just learn those really quickly. If you do, then great. We're going to kind of tackle right in. The first method that's usually taught is called integration by parts, and it looks like this. So the formula for integration by parts is u times v minus the integral v du. Don't worry too much. This is a u, by the way. Don't worry too much about the like what is u and v. We'll explain it right now. But just know this is the general formula you're going to be using. It's derived from the power rule. It's very complicated, so for the sake of everything, you just kind of want to memorize it, and it's pretty standard from there. So what we'll be doing is the integration by parts is used by functions that can't be combined together, and we can't sub them away. Basically, they're different functions. So to give you an idea of what that might look like, let's say our first problem was the integral of x sine of x dx. Okay, so the problem here is that we can't sub it, we can't combine things. We have an x, we have a sine of x, they're different functions. We can't integrate them normally, we can't multiply them either, so we have to kind of tackle this with integration by parts. So the first thing to do, we want to keep this in mind, this formula here, and we want to define four things, and we usually want to make a chart right under our integration by parts problem. So the first thing, we want to define u, we want to define du, we want to define v, and we want to define dv. This is going to help us kind of fill in this formula here. So u is kind of something, you'll pick u, you'll pick dv. In terms of picking u, which is the most important process, because if you pick the wrong thing, we're in a lot of trouble, because it only kind of works really, really nicely in a certain way. So to help you with that, there's this acronym called LEAT, and it's very helpful for most integration by parts problems. So what it is, it stands for a series of things. So the L stands for logs, the I stands for inverse trig, the A stands for algebra, the T stands for trig, and the E stands for exponents. So basically what it's trying to show you here is that the first one here is the thing if you find it in your original integral, that's what you want to make u first. And you're going to work your way down until you find something that is there, and then you'll sort of apply it. So it works like this. If we look at this original expression, okay, do we have any logs? We don't have any logs. Okay, do we have inverse trig? We don't have any inverse trig either. Do we have algebra? Now algebra is it's a fancy way of talking about just any sort of x term, like x squared. We do have an x, we have an algebra. So we're going to make the x our u. So remember, this one is defining our u. This helps us define our u, and that's it, okay? So our x is our u. We're going to put our u right there as x. And then before we do anything else, we want to define our dv. So the two things you'll be defining every time are the u and the dv. So we defined our u. Now whatever's left in our expression with the dx, that becomes our dv. So sine of x dx is going to be our dv. Okay? So after we do that, we have to kind of get du and v, and we do that with our integrals and derivatives. So to go from u to du, we would of course take a derivative. So x's derivative is 1, which we know, and it becomes 1 dx. And then to find v, we have to take the integral, so we can make a little integral here if it helps you remember, of whatever we picked as the dv to find v. So sine's integral, of course, we know is negative cosine. So negative cosine is going to be our v. And if it helps, you always can take the derivative. So cosine's derivative is right, negative sign, and negative gives you just sign, because it's a positive. So that's how you can check it if you're unsure. But that's how we define all our variables. After we do that, we just kind of use this formula we derived up here, and we're just going to go fill it in. So u, we know, is x, as we just defined. V, we know, is negative cosine of x. And then we minus the integral of v, which again is the same thing, it's negative cosine of x. And then we have du. And du is, of course, 1 dx. So we just put 1 dx. Okay, so let's kind of simplify things a little bit. So the negative here can turn into negative x cosine of x, just so it doesn't confuse us. We have a negative and a negative, so we can just kind of move it out here, the sign, like a -1, and we turn it into a plus. And then it just turns into cosine of x. It's positive now. The 1 we don't really have to write anymore, so we can just write it as dx. And now we can simplify this out. So this stays the same. This can't be simplified anymore. So negative x cosine of x plus cosine integral of course is sine, is sine of x. And we just have to, of course, just like always, after we take an indefinite integral, we have to use a plus c. And this right here is our answer. So it ends up being, so the integral of negative x sine of x is negative x cosine of x plus sine of x plus c. So whenever you do integration by parts, you're going to get a series of like a sort of a few terms, at least 2, plus, and a constant of integration as well. And this is going to be how your process works. It requires a little bit of setup, but it generally is okay. We're going to come back and do a few more. I'm going to kind of change it up after each one. I kind of give you a different way of seeing, standard problems. And yeah, be right back. Welcome back. We'll be doing this integral here. Actually, let me make it a 2 so it's not confusing. And so basically, this one is called, will be the integral of x e to the x dx. I'm going to leave this up here along with the formula because I find that they're very useful to kind of reference when you're first learning. So again, we have a situation where we can't really use u substitution. If we had x e to the x squared, we could use u substitution because we could make the x squared into 2x, the x's could cancel, we could pull out the constant, and we could use u substitution. However, we can't use it here because it's an x. There's nothing to really u sub. You won't be able to get rid of the x. And we have 2 different functions as well. So whenever you have something like this, this is where you do have to use integration by parts. So let's do the same thing we were doing before, okay? So let's define RU, RDU, RV, and RDV. And you'll see that after doing a few of them, especially the more straightforward ones, you'll see the process is very similar each time. You'll feel really good about doing it as well. So just like before, let's define our U. We don't have any logs, we don't have inverse trig. We do have algebra again though. We have this x. So we need to put our x as our u. Then we need to, the rest of the function becomes the dv. So that is e to the x dx. It's also fine, by the way, if they're switched. So if the e to the x was over here and there was an x for some reason, since they're multiplying, you can make it the e to the x, the dx can come together down here, even if the e to the x wasn't right next to the dx. It's perfectly fine. So now let's find the rest of the things in our chart. So the du would be 1 dx, similar to last time. Your integral, if you want to put that symbol just to remind yourself, of e to the x to get v is of course just e to the x, because e to the x derivative is also e to the x. Now that we have all the parts, let's kind of plug them all in. So our u would be of course the x, our v would be the e to the x. Then we would subtract the integral of v again, which is of course just e to the x. And our du is going to be 1 dx, similar to last time, right? Okay, so now let's do something similar and let's simplify things, make it a little bit nicer. You'll also find that I put these parentheses here all the time, especially for integration by parts. The reason is just because it's very easy to lose track of signs when things get more complicated. And it just makes it easier to remember all the parts you've added if you've forgotten something. But over here it's fine. So x e to the x can kind of stay. Now there is no other subtraction, so this kind of remains a subtraction. The integral, we can rewrite this as just e to the x dx, because this is of course just a 1. It doesn't really matter. So then we can rewrite this again as x e to the x. The integral of e to the x, we already did that, of course, is just e to the x. So it's minus e to the x. And don't forget that constant of integration, the plus c. And this is your answer. The integral of x e to the x happens to be x e to the x minus e to the x plus c. And this would be your answer to this problem. So as you can see, for the more straightforward ones, they're not too bad to do. They require a little bit of setup, a little bit of knowledge on basic functions, but for the most part, they're not too bad to do. So I'm going to come back. We're going to start doing some different ones that require a little more, I guess, quite a little bit more steps. And yeah, be right back. Welcome back. We'll be doing this function. It's similar to before, but I've changed it just a little bit. And you'll say, wait a minute, that can't be that much different. And it is similar. We follow a kind of similar process, but you'll see that the answer gets a little bit longer. So it's nice to have exposure to what happens when we see this. Now again, it's tempting, but we can't actually use substitution here either. The reason is because we can't use sub this x squared, because we'll be left with an x that won't cancel with any other x. This is e to the x. We can't use sub e to the x, because then we'll still be left with, of course, this x squared. So we can't actually use substitution here either, which means a nice bet is to use substitution when they have two different functions like this. Okay, so the first thing to do is let's set up our chart for u, du, v, and dv. Okay, let's just do what we were doing before. Okay, so just like before, do we see logs? I don't see any logs. Do we see inverse trig? I see no inverse trig. Do I see algebra? I do see algebra again. This x squared is still an algebraic term. So let's put x squared down as our u. The rest of the function, of course, becomes our dv. So e to the x dx. Okay, let's find the rest of it then. So x squared's derivative turns out to, of course, be 2x dx. And u, just like before, if we take the integral of e to the x, we get e to the x again. So we've got our chart, not too long it took. Let's then write everything out. So we have our u is x squared. We have our v, which is e to the x. Then we're just going to fill in the rest of it, right? Minus the integral of our v again, which is our e to the x. Not too bad so far. And we have our du, which is 2x dx. So 2x dx. We've run into a problem though this time. It's not just one, so we can't just focus on one function. And this is another sort of integration by parts problem, isn't it? Because with e to the x, we have 2x. We can't use sub anything here either, because we won't be left with, we'll still be left with some sort of function. We can't just get rid of one. There's nothing to sort of cancel out all of the u's. So we'll still be left with some sort of u function. And so because of that, we need to use integration by parts again, which is something you'll see which is kind of common when the x is bigger than a power of 1. You typically won't see something bigger than a power of 2 unless they're being a little bit mean to you. But the way it works is still the same, so we're going to rewrite this, as this won't change. We're going to keep the minus. The trick is we want to use these brackets here because it's going to get very complicated with all the signs at times. We want to make sure we aren't losing track of anything. So we're just going to apply the integration by parts again to this section because we can't solve it just by normal methods. We still have two functions. Okay, so let's, off to the side here, let's make another integration by parts chart. So over here, our u can of course still be the algebraic term, this 2x, so let's make a note of that. And then our du can be the 2 dx because the derivative of x is just 1. And then our dv can of course be everything else, our e to the x dx. So our e to the x dx. And just like I said before, we can take the e to the x and dx, we can put them together, it's perfectly fine. Then we're going to take the integral sort of this e to the x. We'll get that v is equal to e to the x. Now we have the whole chart, so let's kind of put it together. So everything we're going to put after this is this just integration by parts. So our u for this part here, the u is, of course, the 2x, so we'll put the 2x here. Our v is e to the x. Okay, so just the same as before. We're just kind of using it again. We're just repeating integration by parts. And then our v is e to the x once more. And then our du is, this time, is 2 dx. So 2 dx. So now we can work with this. This is fine. So we're going to rewrite x squared e to the x. Then we're going to keep the brackets for now because we're going to need to distribute this at the end. We're just going to write this as 2 to the x, e to the x without the parentheses because they can't simplify any more than this. Now we're going to do something here to make it a little bit easier. We're just going to take the constant out. We can do that. There's no reason we can't take the constant out as we normally would in basic integrals. Then it just becomes e to the x dx. And now we can do this, right? So we're going to rewrite this x squared e to the x. This stays the same, the 2x e to the x. And then e to the x integral is, of course, just e to the x. So we have 2 e to the x. And then we've simplified everything. It's technically fine if you remember. Just remember that the plus c always kind of remains separate. We don't really. It can be any constant. So we're going to put it on the outside here. And then we're going to distribute this negative from all the way up here to finalize it. Now just remember to do that because if you don't, the problem will be incorrect. So of x squared e to the x, this is a positive here, so this turns into a negative 2x e to the x. Now we have a negative and a negative, which turns into a positive 2 e to the x, and we have the plus c. And this would be your answer. So it turns out the integral of x squared e to the x is x squared e to the x minus 2x e to the x plus 2 e to the x plus c. And you're going to see that this kind of natural progression where you'll see this x power reduce and reduce. So that would be that one right there. And we're going to be back for another one. For the last bit of things, we're going to try something that looks eerily similar to stuff we have been doing, but it's going to require a much longer process to complete. So the function is going to look like, it'll be something like e to the x sine of x. And so on the surface, this won't look too much more difficult than a normal function, but it's going to end up taking quite a lot longer to do. And the reason is because really we have two functions and one of them isn't an x, so it's going to be a little more complicated to find an answer for, but we will use the same process as a roundabout to get it. So what we'll do is we're going to start off the same, okay? So we're going to make our u, our du, our v, and our dv chart. So let's do what we normally would be doing. Let's find this u. So we don't have logs again. We don't have inverse trig again. We also don't have algebra this time, though. We have an e to the x, we have a sine of x, we don't have any algebra, so we have to move down again. The next one is trig. We do have a trig, though. We have sine. So we're going to use sine as our u in this case, which makes the other part, e to the x dx, our dv. So e to the x dx. So now let's do the rest of the chart. The derivative of sine is cosine, of course. And v, we would take the integral of e, and we'll get e to the x as our v. Now let's put it all together in the formula we've used quite a few times. So our u is going to be the sine of x. Our v is going to be e to the x. We're going to subtract our v, which is still going to be e to the x. And our du is going to be cosine of x. And I apologize, there should have been a dx here. Cosine of x dx. So if you don't see the problem, just like before, we had this integral at the end, and we can't simplify this normally again. We have two different functions. We're going to have to use integration by parts again. What you're going to find with these problems is when there are multiple functions that look like this, they're going to kind of repeat, and you'll see what I mean. And there's a little trick that we'll use with them. So we're going to rewrite this, of course, as just e to the x sine of x, since this one won't change. This one, though, we have to use the bracket method again because we have to use integration by parts here. I'm going to do it off to the side over here just so that you can see it. So u, we have du, we have v, we have dv. Okay, so just like before, our u should be the trig component, so the cosine. So we're going to make u equal to the cosine of x, and we're also going to have the e to the x dx become the dv, so e to the x dx. So similar to last time. Then we'll have the cosine. So cosine's derivative is, of course, negative sine. So we're going to put in its negative sine. And the integral of e to the x to give you v is going to be just e to the x again. So now we have to put all of this in. Our u would be the cosine of x. Our v would be the e to the x. We're going to subtract the v again, the integral of it, which is e to the x. And then we're going to have the du, which is going to be, when I posited it again, it should be negative sine of x dx. So it should be negative sine of x dx. Okay? Now what we're going to be doing is we're just going to kind of simplify it a little bit. But we're just like before, we can't really get rid of these brackets. We're going to have to do a bit more work with it. So we're going to have e to the x sine of x. We're going to keep this on the outside. We'll keep this the same. For the sake of clarity, we're just going to go ahead and get rid of the parentheses here. We have enough parentheses kind of going around, so we're just going to combine this. And then what we're going to be doing is, if you notice there's a negative here, there's a negative here. So we're going to take out this negative 1, and the negative will multiply to become a plus. Then we're going to have e to the x sine of x dx, of course. And what we're going to do next is something that, or relatively, with like pretty soon, it's going to be a bit interesting. And once you see it, you'll say, wow, how did I not think of that? So before we do that, though, we're going to go ahead and distribute this negative in here. So it'll distribute into the positive e to the x cosine to make it a negative. And then it's going to distribute here to make this plus a negative. Integral of e to the x sine of x dx. And now it feels like we're stuck, right? Because we have this e to the x sine of x. It feels like we can do integration by parts again. We're just going to get the same integral, or the same integration by parts up here. If we did it again, it's not really getting rid of anything. We can't simplify it, and that feels weird. So the thing to do, whenever you get to something that repeats, kind of has like a cycle nature to it, we're going to do this one trick. So if you notice, the integral of e to the x sine of x dx is your starting integral, right? It's the same exact thing. So what we're going to do is, when we write this equal here, what is it equaling? Well, it's equaling this up here, right? This integral is equal to all of this, all of these terms here. So we're just going to put it here. That's all we're doing. We're going to put that the integral of e to the x sine of x dx equals to just all of this here, which is true. It totally does. Okay, so what do we do now? Well, the trick that you just kind of have to know is, because this and this are the same, so it's kind of like x and x, right, where we can move them around. They're the same exact term, the integral. We're going to move this to this side, which is a perfect algebra thing to do. There's no reason why we can't do that. So we're going to add the integral e to the x sine of x dx, okay? And that cancels it, right? Just like normal algebra. And then we're going to add it to this side too, because if we add this, we have to add it to this side as well. So we're not doing anything. We're doing the same thing to both sides of this equation. Okay, so we're adding this. Okay, so this one cancels. Now if we have two of the same term, think of this like, x, and when we're adding an x, what does that become? That becomes 2x, right? Same thing here. This becomes 2 integral e to the x sine of x dx. I know that looks weird, but it's perfectly true. This is a true statement. So it's 2 of this entire function equals to everything that's still here, right? E to the x sine of x minus e to the x cosine of x. Okay? Now what we do is, because we want to know what this integral equals, right? Not what two of them equals. So what would we do if we had 2x equals to a function? Well, if we wanted to solve for the x, which would we do, this function, we would just divide by this 2. So we're just going to divide by 2. That's all we're doing, okay? Then we divide this by 2, as we would in a normal algebra problem. So we'll get to the integral of e to the x sine of x dx, because now there's a 1 here, equals to this. Now, usually what teachers will want is they'll want you to write this as sort of a constant in front of everything. Now, it's technically the same thing, but some teachers are very particular. So you'll go ahead and turn this into a 1/2, because this is technically 1/2 is the same thing as the whole thing divided by 2. So 1/2 times e to the x sine of x minus e to the x cosine of x. And remember, because now that we've kind of gotten rid of the integral in kind of an interesting way, but still the way, we just add this plus c. It's still an indefinite integral. And this is the answer. Now you could rewrite this. It's just this being the answer again. You don't have to. You also could take out an e to the x. There's many of these problems that I showed you even before where you could have factored out something. It's really not necessary, but you can do it. There's nothing wrong with it. But this is the answer. So the integral, or the answer to the integral e to the x sine of x, it appears to be, at the very end, the 1/2 times e to the x sine of x minus e to the x cosine of x. So it's a very interesting process, but this is the hardest they really get. There is certain cases where at times they'll give you a constant. There's some sort of linear term in the x, like maybe say sine of 4x e to the 2x or something like that. To make it a little more complicated, you have to balance a bunch of constants going around, but honestly, that's kind of as hard as they get. So I just wanted to show you kind of in this quicker video all of the very basic integration by parts method, breaking them down.